Quantum Physics in the Australian Bush is a series of tutorials produced for science, innovation, communication at schools. When talking about quantum physics, we had discussed that some of the particles, electrons and protons, were made in the Big Bang. Then we got your question of the day is, how big is the universe? Well, the universe has not always been the same size. In fact, it started off as a tiny dot, much smaller than a proton. Then, with no time whatsoever, in an instant, we called inflation, it suddenly grew from nothing up to the size of a golf ball. After that, which happened in under a second, it continued to expand. And over the next 380,000 years, this fireball expanded until it became transparent. And at this point in time, it had a radius of 43 million light years. Now, we can actually see that point in time where it went from solid to transparent. But I thought I'd stop and look at and ask the question, given the mass of the universe, well, what time was it the mass of a hot lump of coal, an ember? And if you get a chunk of coal out of your fireplace, and that's what it looks most like, just a glowing ember, at that point it was 31 light years radius. It's worthwhile to stop now and consider what a light year means. Now, if you multiply speed by time, you get a distance. So a light second is roughly the time it takes for light to travel from the surface of the Earth to the Moon, and it takes about 8 minutes for light to travel from Earth to the Sun. So the Sun is 8 light minutes away. We get down to Proxima Centauri, our nearest star. That's 4.3 years of light travel. That's 4.3 light years away. So just to review, a light year is a distance, how far light travels in 1 year. So the universe, some 380,000 years after the Big Bang, underwent a critical transition from an opaque fireball or black body radiator, which looks a bit like our sun, to something that was transparent. So this critical time is where we can, after which we can look back through the transparent universe to see the old untransparent universe. So anytime after that, we can always look back, and we can look back now and see the ancient universe, which was in fact 1,000 times smaller than our current universe. So what does it look like? What would it look like? This should seem familiar. This is a black slide. It's also the black sky we see. So this is our fireball seen with our eyes. The wavelength has expanded a factor of 1,000. So our next slide will show us what it is color corrected. Here we see it color corrected, and in fact it's rather boring. It's completely white. The actual wavelength which we see now color corrected is a 2mm wavelength. So this is in a sense a false color image. So this is 2mm microwaves. So it was really a rather sad news story. We went up and photographed the Big Bang at the start of time, or the recombination at the Big Bang, when the universe suddenly went from solid to see-through, and it was perfectly white. So the first thing we did was we converted it from white to a false colour, which is in this one orange, and then we noted that there was a swirl in it. We subtracted the swirl from it. And then we noted that we could see the galaxy. We corrected that again. And then we finally had our corrected colour of the tiniest deviations. These are the smallest deviations. So the red is just the smallest bit hotter, and the blue is the smallest bit colder by over a factor of 1,000 or 10,000 difference. So if it was a cup of coffee at 90 or 100 degrees, this would be seeing differences in 0.01 degree. I've been fortunate to grow up with a series of rockets and improved telescopes which have mapped or photographed the recombination of the Big Bang 380,000 years after the Big Bang. And this one is a real beauty by the Germans. It has, you can see the mirror in there, but it's got onboard liquid helium to freeze down their cameras so they can actually see this. And it's taken, I think, about 5 years just to take one image. It's the most expensive photograph or most expensive selfie ever. And of course they put a lot of computer enhancement to convert it from just a blank sheet of paper you'd get out of a broken printer to this fantastic image. And you can see the satellite sits up in space and just really scans each point of the heavens as it rotates around. Fantastic piece of kit. Thank you, Germans, for putting this up. But the real story here is that practically when they photographed the Big Bang, our picture of the Big Bang or recombination event as the Big Bang cooled down, finally became transparent, it's really just like living permanently in the centre of a gigantic ping pong ball, and this picture shows what it's like. This is where my expertise as a teacher possibly comes in, knowing how to select a model or an example where you're not getting people to stretch too much. Now, I've taught you what a light year is. Now, if you pick a hair from your head, the width of that hair is 150 micron, which is 150 millionths of a metre. Now, if we said that a hair is the width of a light year, so the model we build, a hair's width is a light year, we have a new sort of scale, a really useful sort of scale, and I've called it the HHow scale, hair equals light year scale. So we can use that scale as we have a map. The actual dimension of the map is not the actual size, it's one hair equals 1 light year or 1 millimetre equals a kilometre, depending on what the scale is. So let's see what we get out of this. Here we get the rather useful version is that the model of our universe, if we built it, is the actual size of our Earth. So at this scale, our universe is the size of the Earth, and fortunately every point now is in the very centre of the Earth, so we can't actually ever get to the surface of the Earth. We're always forever in the centre. No matter where we are in the universe, our past is a certain distance away. So with the HHow scale, if we built a HHow scale universe, we'd build it. It would be the size of the Earth, and there's a lot of convenient things about that. One of the best things about it is that the universe from 380,000 years ago would look like the cloud layer that we see in the sky. So if we look up, there'd be a cloud layer, and there's an area where there's nothing there, and that corresponds to the dark ages where the cloud hadn't condensed to form galaxies. So from the ground level downwards, you have galaxies and stars beginning to form. So putting that model aside, we have in reality the situation where we have actually potentially 2 cloud layers if you think about it. So we have you, and in the centre of your head is the only position in the universe where you know now. So it's now there. Now on Earth we have a cloud layer, it's at the ground, and above it is a cloud layer, so it's clear to the cloud layer. Go a bit further, up to 100 kilometres into space, and then you have stars, moons, galaxies and everything. And if you go higher and higher, 46 billion light years higher, space ends. But before it ends, there's a layer where the dark ages go, and there's no stars, and because we're going backwards in time where the stars and galaxies hasn't formed. So if you're in this area of space or looking at this area of space, there is nothing there, but eventually you reach this layer as you go back in time where the universe looks like a cloud, a very uniform white cloud. And behind that, only a short distance behind it, is the start of time. So you can't go further than that. So indeed, there's actually two cloud layers. The Heli model is probably as good as any other model, but it's got a lot of problems. But let's talk about some facts that we do know. We are pretty sure that there's 200,000 million galaxies in the universe overall, given what we can see and have able to see and counted. And just to put that into perspective, there's actually more cells in your body estimated recently. So at the Heli scale, getting back to that, the actual thickness of the Big Bang cloud layer, and that reduced thing, is around 54 metres. There's a lot of problems in this calculation. But the area of clear universe with no stars in it is around 83 kilometres. So that would be from the cloud layer to where the ground begins. Now remember, of course, that you are always fixed in the very centre. So, as I said before, you are always in the centre of the universe. So everybody is in the centre of the universe. It's very democratic that way. If you see a distant object, you're seeing into your past. So you can only ever see into your past. You can't see into the future. If you move towards the object, you move into that object's present. And where you were falls into the past. The edge of the universe, the first point of time, is always getting further away and deeper into the past. No matter where you go, the start of the universe is in your past that length of time. In summary, the answer to how big is the universe and how do we know about it is, well, we know about it because we can actually see all the way back to the cosmic microwave background of the afterglow of the Big Bang. Now this background is 46,000 million light years away. It looks like a cloud layer, and we know that the start of time is behind this cloud layer. So we can see the entire universe and measure how big it is. Thanks for listening. I'll hope to improve this as I get feedback on it.